Now for put options, really nothing is different other than the exercise price. Instead of using the maximum of 0 and the stock minus the strike, we use the maximum of 0 and the strike minus the stock. So as an example, using that same 1-year lattice, if we were pricing a European put with a strike of 40, you can now see all that's happened is that we've changed the exercise values to reflect a 40 put, 40 strike put. The other thing you might notice is that the put deltas are negative. This goes back to a comment in an earlier module where if the exercise value goes down when prices go up, that's a negative delta. And indeed, we see throughout that anytime we're holding stocks, the delta position is negative. We're shorting stocks and we're going long T-bills. And then the calculation of put prices at each of the various nodes on this lattice proceeds as before. Exactly the same formulas, only starting with a different set of exercise values. The equation I generalized at the end of the prior module can be generalized further, and this is the formula here. It's not a formula in the chapter, but it's a useful one for pricing European options using n steps in the lattice. And what you'll notice is structurally this formula says, first of all, take a present value over the entire period. So we're starting at time little t, and we have an expiry at time capital T. So we have a present value, and this summation, although it can be a little imposing, you're probably familiar with the binomial distribution. If we have n steps from initial time little t to capital T time, n steps will produce n plus 1 stock prices, and those n plus 1 stock prices will each be defined as the initial stock price times some number of U's and some number of D's, where the total number of U's and D's is n, because in each step we're going to pick up a U or an n. So we have the exercise value of the option at time t for each of the n plus 1 stock prices, and then we see these are the binomial probabilities of each of those stock prices prevailing. And this generalizes the earlier two-step binomial. So as an example, if we wanted to recalculate these 3-period options, we have a P star of 0.42. We could go directly from the European exercise values to the price, and what this formula would say in this instance is, first of all, let's remember what these binomial coefficients are. N factorial over j factorial times n minus j factorial. You may remember these as combinatorial coefficients. Sometimes this is called n choose j. And you may recall Pascal's triangle, which is an easy way of coming up with the collection. You start with a 1, and then each row is the sum of the numbers above it. So we have 1, 2, 1. The next row is 1, 3, 3, 1, 1, 4, 6, 4, 1. And these give you the collection. So this is the collection of values at row 2. 2 factorial over j factorial times n minus 2 minus j factorial, and so forth. So these binomial coefficients, or these combinatorial coefficients, come from the coefficients of a plus b to the n. So when you have a binomial and you multiply it out, you get these. So these would be the coefficients of a plus b to the 4. So these are the coefficients that I need for the 3-step lattice. And what I would finally get is that the price, which was 7074, is the 1-year present value. So it would be e to the minus 3 times the period discount rate. And then I need payoff. So first of all, I have P star cubed times the exercise price of 34,678. I then have, and we know that from the earlier slide that P star was 0.4253. So you can do this and you'll see that it works out. The next coefficient is 3 P star squared times 1 minus P star. And the exercise value in that state, where there's 2 ups and 1 down, is $12.81. And plus this, and then we have plus 3 P star times 1 minus P star squared. Now the exercise value there is 0, and the exercise value in the down state is also 0. And you can see easily that this calculation in general would be much quicker if you're calculating the value of the European option than going through backward substitution. The advantage of backward substitution is that while you're doing that calculation, you can also get the value of the replicating portfolio at each step, whereas by going directly from expiry values to the price, you have no opportunity to determine what is the replicating portfolio. You can only do that by using a backward substitution methodology.